how to model a transfer function in MATLAB Simulink, which is a very good software. So let's keep this. This is a second order. By the way, this is a second order. When you see in the denominator, when you see power square, then it is second order. Suppose there is another transfer function x2 of s 1 over s plus 1. So this, by looking at this transfer function, this is the first order transfer function, and this is the second order. So I will model these two systems in Simulink to show you how it looks like. So if you go open your MATLAB and give the command Simulink, which I've already given. So when you click on this Simulink, you will see this window. So after you go to this window, click on this library browser, you will see multiple options here. Go to commonly used blocks and drag some of the blocks in it. So I will say you drag this one, this is the gain, and then drag this signal, which is the signal multiplexing, like two signals coming in, number of inputs coming in, number of output is just one. And then you need a step value. Sources, go to sources and click on the step function, which is over here. You need this one here, so I would make this one here. You need a transfer function. So in order to see the transfer function, go to continuous. You see this is our transfer function, and this would come over here. After the gain, the transfer function comes over here. Then you need a summation block. If you take a look at the block diagram for this simple block diagram, you need a summation block as a feedback signal. So what I would do, go over here, and this is a summation block, comes after the input, which is a step, and I would change the signs here, plus and minus, and then I will join them. This one is the signal coming in, input signal and output signal. I will connect with this one, and then I need a scope. How would I see the simulation? So I need a scope which is inside the you can take a look. The scope is inside the commonly used blocks as well as in the sources, sinks. If you go here in the sinks, you can find the scopes there, but commonly used blocks are most of the time they have included all the small important functions with the library. So you join this over here, and then you would connect this with the, you will wire the branch of the input to see the input, as well as you will connect this with the output. Now this is a complete model. So if you want to see the answer for this one, so let me run this, running for stop time for 10 seconds, how the simulation looks like. If you go over here now, after it has completed simulation, double click on the scope, you will see this is the for the timer. The yellow color line is the output response of the transfer function, and the blue color line is the reference value, means the step value has been given, which is on the left hand side. So now I would change this to according to my model. Like I want to plug it this value, this one, I'm sorry, this is the one, 2s square 2 plus 2s plus 400. So what I would do, I will double click this model. One is a numerator, so you just write down the coefficients in the order, decreasing order, 2 to 400, and hit apply. If it is not visible, you can just enlarge it, and then you can just drag it here to make it more nice. That's it. You can drag it, this one. I'm not sure why the two wires here. You can redo this over here. Now I want to run it to see what is the response. So this is quite small, so what I would do is just zoom in this portion. You see it's quite wavy response. So because the damping is so small, that's why it's a undamped. This response looks like an undamped system. So what I would do, I would just copy this Simulink snapshot. Somehow you can copy this into your, or maybe print a figure, and then you just edit, copy figure, and bring it in your notebook here. Oh, the background is white. I think you can play how to change the background later on. So let's see. I want to increase the damping here. Damping is the second factor, which is 2 right now. I can increase to 12 to see what is the effect of damping. Then run it. You see, when I increase the damping coefficient, now the response is quite stable. A little bit overshoot in the beginning, but that's fine. And we see the mass comes back to the normal, like 2.5 into 10 to the negative 3. So you just print it to figure, maybe print preview. So okay, that's how you will just do this. And this is our lab 6. You see the difference between this and this, right? Clear.